What I was saying is that basically starting today and now, because we're a little bit or quite a bit late, we may not finish, and maybe that's not a bad thing because there's not that many people here, and there's even fewer in Daytona Beach. But basically, we've gone through from the beginning, we've talked about a lot of different steps. And then we looked at a number of different algorithms. And kind of the purpose of this final discussion beginning today, before you begin your projects, is how do we put all of these pieces together? So I'm kind of putting it into, I call it like a pipeline. We're going to start on one end with generating the data, and actually the more you understand about how the data is generated in the first place, the more you can understand possible issues and problems with the data, because your results of your analysis, in particular classification, we're going to be doing supervised classification for our projects, ultimately depend upon the source of that data and how all the original data is generated to begin with. That's why before I turned on the system here I was talking about, when we did bioinformatics, we actually went into the laboratory and did the experiments. And you could see, what are all the issues that crop up as you're generating the data before you even put it into a form. And there it's not a code like CGAT for your genomic sequence. It's still like Petri dish type stuff. You're getting the DNA base pairs physically. And then, that's ultimately where you're starting, and now how are you going to take that and translate it to something that so there's the issue from the scientists generating the data to begin with. So if you think in terms of meteorology data, well, it's going to depend on all those sensors and how are they generating the data that you want, and what are all the possible sources of errors just that can crop up before we even look at the data. So I'll put this full screen now. So I'm going to start at that end, and then we want to finish the pipeline at the other end. Your final raw data, here's the classification, here's how you did, here's the evaluation of our results. How good a job were we did, how good of predictions is it able to make, how much can you count on it, and so on. So starting at the one end, we're gathering and understanding our data. Again, this is kind of a review going all the way back to day one of the course, right? You have to evaluate your various sources. How is the data determined? Where are the possible errors? And errors have a bunch of ways of cropping up. You're in the lab, you're measuring the amount of material using a pipette. Sometimes that's computerized, which is going to eliminate sources of error. But even then, there's some variation. Calculation errors. And calculation errors can be stupid mistakes like 2 + 3 is 4.
Master. Missing a negative or something?
You drop a negative as you're calculating. Calculation errors can also be, you put it in an Excel spreadsheet. And I remember a few years back, there was a known issue. Excel made certain incorrect, it only affected some tiny percent of the results, but there was one type of error that it made. I don't know if anybody remembers that. And it wasn't caught for a long, long, long time. So your calculation errors may not be an error on your part. It could be an error on some equipment that you're relying upon. That would be probably an unknown error, not something that you would necessarily know. I mean, if you catch your error, it's a known error. But transcription errors, you write it down in the lab. You would write down, it's supposed to be ACC, and you write it ACT. Or you flip the letters or numbers. Or you put the decimal point in the wrong place, but when you come back to it, you don't see it in the right place. So all of these are, potential problems. Noise, duplicate values. So if you recall, and I really tried to stress this concept through the entire course, know your data. I don't know if you remember that. I kept coming back to it periodically. So once you've understood the source of your data, you're going to now try to take that data and work with it, preparing your data. I mean, you're going to want to analyze it. Do you see anything that obviously looks like maybe wrong, out of place, outliers? Maybe another source of error, you're writing in an Excel sheet and maybe you miss it and go over into the wrong field at some point. And you continue that pattern. In other words, it gets shifted, all your data is shifted. Okay? Now, what are you going to do with it? That's a whole nother matter. I mean, can you rely that that's what happened? Or maybe you shifted down a line or something. Right? Depending on how, again, the more automated that you can do this, the less chance of errors happening. But they happen. What are your features? You get this data set. And what do all the different attributes or features measuring? Try to really understand what those measuring. And because when you come back to that, does your answer, do your results make scientific sense? One of the things I did, this was in a different course, but it was another time I used some data mining techniques to analyze biologic data. It was to determine, evidently, calorie restriction tends to lead to life extension. I don't know if there's some sort of correlation there, not necessarily a causation, but there's a correlation. And the question is, why? And we ended up with some results. And I'm like, I'm not an expert in that area. So I brought in a biologist and I asked her, I said, does this make any sense? Would this be possible cause, or would this be, does this correlation sound right? I would have no clue because I don't have that background, right? So that's I think it came out, yeah, that would actually make some sense. I mean, how much? Is it a causation versus just a correlation? I don't know. But, you know, that's the idea. What do the features represent? Right? What is it that you're measuring? And what form? So this goes back again to the beginning of the course when we talk about the various data types. How are they being measured? Are they binary values? Are they qualitative or quantitative? Are they continuous or discrete? All those issues. So we're going to come back to that, and the reason you want to know that is because those are going to help us choose different algorithms. And one of the questions that when we did the first quiz, after that first quiz that I heard was, well, how do you know what algorithm to choose? And that's going to be one of the things I'm going to come back to later on. Probably not in the remaining time.
Yeah.
So you know, it's basically we're going again in this pipeline, and we're slowly going through this process. And probably the bulk of the time, and you're going to discover this, is spent before you get to Weka or Moses.
Yeah,
Okay? You have to prepare the data into a form and format that the algorithm that you're going to use can actually take advantage of.
What tools do we have to do that?
I will talk about that. We can develop tools. I can develop tools. We can have people do that if it's necessary.
Yeah.
I've not actually seen the data sets yet, but I'm going to see it hopefully this weekend according to the email I just got.
Okay. So hopefully we can just convert the files to a different type, like a data file or something?
Right. It's going to depend on exactly how the data looks. Now, some of the data I've seen from NCAR, again, it depends which form where you look for it. So getting back here, so what form is your raw data?
Right. Okay.
Right? And I'm not gonna do, I mean, some of the data you sometimes see as visual data. And that's really much harder to work with.
Yeah.
And what we're really gonna be looking for is some sort of text data. And I'm not gonna start us with graphical text data, because generally all that graphical text data is actually generated, graphical data is ultimately already generated from text data. So
right.
If you do have graphical data, you should be able to find the text data that generates that graphical data.
So you can also take graphical data and easily turn it back in text data just by...
I don't know how easy, but
yeah.
you can. Right. That can be done, but
I feel that would be a pain.
Ultimately, you're going to just go straight to the text data, and we're not going to start there. And then the other question to ask, okay, we have the form of the raw data. What form should your final data take? And that depends ultimately upon the algorithm you're going to choose. And it can help you choose that algorithm. Maybe it's already in a form that goes straight into decision trees, just to choose an algorithm at random. Okay, well, then if you're going to do that, maybe decision trees isn't the one you really want to work because you don't think it's going to give you as good of results. But hey, all you have to do is throw it in. right? Let the computer crunch, see if you get any good results. So you see how, if it's already in a good format, I mean, there's no reason it can't hurt to just try it. Even if you don't think it's going to give us good results.
Weird. So why would the different forms, like how many different forms can we have our data in, I guess? I'm just thinking like text files, data files.
Well, I'm not talking about that. I'm talking about your attributes. Now, I've used Moses a lot, so I'm going to talk about that. I know that they've been working, there's a team that's been working on generalizing the types of input data that Moses can take. But the last time I actually worked with it, everything still had to be binary. Okay. So now if you have continuous data, you're going to have to prepare that data.
Yeah.
You're going to have to binarize it.
Weird.
Okay. So that's what I mean. The algorithm's going to constrain what you do.
Okay, so if we have continuous data, we have to...
You have to process it.
Like discrete, I guess.
Right. Right.
Discretize it and then convert it into binary. Yeah.
Well, binary is a particular discretization.
Yeah.
Well, yeah.
Into two categories. And how are you going to choose to do that will also matter. And it's usually not that hard. I mean, usually something like that we can do within Excel.
Yeah. Yeah.
And that's not hard.
Take something that's continuous and turn it into discrete edge, kind of.
Well, I mean, you can say if it's above some threshold, it's a 1. If it's below that threshold, it's a 0.
Kind of think about it like when you're rounding for the greatest integer function, that those are taking continuous values and making them discrete.
So I'll pick up from here on Monday, or maybe review some of this again. But these are I set up this whole spreadsheet. I didn't know where to put it, so I put it in as a summary, putting everything together within the advanced techniques. To help guide all of us, once we start the projects, as you proceed through the projects. So you can see, okay, have I asked myself this question? Have I started looking at this? So that's kind of the purpose of this PowerPoint that I just put up on the DataMind website. So with that, does that get you started thinking about how we're going to do this whole process on Monday?
What kind of data is it again? I'm sorry.
Well, a lot of I haven't. So I know that and I might do, and I'm also thinking of having it all 3 groups use the same data, precisely because from how it's been described to me, we've got raw data at one level. We've got semi-processed data.
Okay.
So if you're having if one team's having difficulty processing the raw data into the next stage, we can all start at the same level playing field for the next stage. And then there's might be a normalization, binarization. So the data that I'm going to be getting is at various stages for the same problem set along this general pipeline. So
interesting.
So that's going to be the goal, and I think that I might just have everyone use this genetic expression data, because it does have, we do have it at various stages of granularity, various stages along the pipeline. So that if you get stuck, okay, maybe you couldn't get that part, but that's not going to now mess you up for the next stage, right?
Okay.
So I'll leave it there, and we'll pick up with this putting everything together concept on